Welcome to Chapter 4. We're going to have three parts of Chapter 4. The first part is going to be about discrete random variables, in particular, how to define discrete random variables and also expectation. Okay, so let's get started. We start with random variables with the definition. A random variable, we usually use a capital letter. Here we're using capital letter X, is a real valued function on the sample space S. Okay, it might sound a little vague, but we have been working with random variable for a while by now, even though we didn't realize it. So let me use this example. Let's just say our sample space, okay, capital S, is what we call A, okay? And you can see that A consists of two things, A1 and A2, and they are the 36 element space resulting from rolling two fair six-sided dice. Okay, so A1 is the outcome of dice 1, and then A2 is the outcome of that of the second one, okay? So notice here, we highlight that random variable is a real valued function. Okay, so it's gonna be a function. And we're writing here as A as the combination of A1 and A2, okay? But exactly how, we are having three examples here that all of them are random variables. Okay, so the first one, the random variable is just the outcome of the first die, okay? And it could be 1, right? 2, 3, 4, 5, 6, okay? We know that. And then we can also have random variables such as, what if I want to know the absolute difference between the two outcomes? Then I can define my random variable in this way as well. So notice the first example, we're using capital X. The second example, we're using capital Y, but that's also a random variable, okay? Any letter you want to use is fine. And the third example here is looking at the sum of the two, which I think we covered in the introductory lecture at the beginning of the semester. Okay, so all of them are random variables. Okay, they're all real valued functions on the sample space. A few things to keep in mind. Random variables, really, you can think of it as a number associated with a random experiment. Okay, the experiment here is that we're throwing or we're rolling for a two fair six-sided die. And then the outcome, either it's just the first, the outcome of the first row, which is a random variable, or the absolute value of the difference between the two, or the sum of the two. They're all random variables, and they are really just a number associated with the random experiment, okay? And I would also mention, just like I was saying earlier, random variables, really, you can think of it as a fancy way of describing an event, okay? So remember our X, okay? This random variable is just the outcome of 1, okay, A1, which is the first die. Then what we have seen before, we've been using this kind of expression, right? The probability of the X equals to 1, the random variable equals to 1, is just the first outcome becoming 1. And then that probability, since we know that it's a fair six-sided die, so we know that it's going to be 1/6. Okay, so this is what we mean by it is a fancy way of describing an event. And just keep in mind that random variable is random, okay, but it's still a real valued function on the sample space. And you can define random variables in all kinds of ways depending on what you're working on. So let's turn to the exercise here. A coin is flipped until a head is obtained. The flips are independent, okay? So keep in mind independent events, okay? Meaning that any particular flip does not affect any other flips. The flips are independent and each one has a probability P of heads. Let the random variable X denote the number of flips until a head is obtained. Okay, so take a moment to think about what we mean by this random variable, okay? And think about how many possible values, like the sample space of this X could be, and then how we can work out each of one for the probability. Okay? So X is the number of flips a head is obtained. Okay? So it's possible, right, that X equals to 1, okay? And the probability of that, well, if we think about it, it would just be the probability of getting head on the first flip, and that will just be P, given that we know the probability of heads is P, okay? So possibly X could also be 2, okay? To have that happen, we're gonna have the first one is tail, second one is head, okay? Which now we know is 1 minus P times P. 1 minus P is the probability of getting head getting tail in the first row, first flip, and then P is the one getting the head on the second flip. Okay, they're independent, so we multiply them together. Okay, we can keep going. Okay, so generically, if I want to know the probability of x equals to any value n, then that means we need to have the first n minus 1 flips to be tail, and then the last one to be head. Okay, and we also know that, okay, that will be 1 minus p, that's the probability of getting any flip as a tail, to the power of n minus 1, because we have n minus 1 of it, okay, and multiplies by p. Okay. Actually, as you can see that you can keep going. Okay, so here, this random variable, okay, is a real valued function, okay, and at the same time, the sample space is actually infinite number large, because you can just keep going, like just very unlucky that you're always getting tails. But we're showing here generically that for any x, for x to be equal to any n, you're able to get expression for it, okay? So for us, this example tells us that, well, we have to think about the sample space of x, okay? Because remember, random variable is a real valued function on the sample space, like what we defined earlier in the definition, okay? And then the next task will be thinking through carefully about what are the possible values that the random variable can take, okay? And then for us, we actually also interested in the associated probability for each of this, okay? And later on, we're going to define all of this more carefully in terms of distribution.